Okay, so I would like to discuss how to generalize the ideas of finding fixed points and stability that we talked about in class for one-dimensional problems, that is, for problems of the form dx dt is equal to a function of x, to two-dimensional problems. And so this on the screen right now is sort of a typical two-dimensional problem. So we have one equation for dx dt, where we say that dx dt is equal to some function of x and y, and another equation for dy dt, where dy dt is equal to some other function that I've called capital G of x and y. And the question is, how do we proceed in our analysis? And the game is exactly the game as what we talked about in 1D. There are two steps. So there's step 1, which is to find the fixed points. And the way you find fixed points is exactly analogous to what we did in 1D, namely a fixed point is any position which is now going to be a function of two coordinates. So I will call the fixed points x star and y star, such that f of x star and y star is equal to 0, and also so that g of x star and y star is equal to 0. And if we can find any x that satisfies these two, then that would be a fixed point. So I'm going to, in order to make this a little bit concrete, I'm going to go to an example, and we'll sort of go back and forth between the abstract formalism and an example in the hopes to show you better how to do that. So here's an example. So this is a set of two equations. You'll notice that this right-hand side, x minus y, is what we called f before. So this is f, so that's f. And this x squared minus 4 is what we called g. So in order to find the fixed points, what we have to do is set both f and g is equal to 0. So if I set f equal to 0, so f is equal to x minus y. So if f is equal to 0, then that implies that x is equal to y. And similarly, if I set g equal to 0, so g is x squared minus 4, so when g is equal to 0, then that means that x squared is equal to 4, or x is equal to plus or minus 2. So so the fixed points have x is equal to plus or minus 2 from the g equation, so that's this equation, and we have x equals y from the f equation, and so that means that y also is equal to plus or minus 2. So what we've just discovered is that this system has two different fixed points. Let me put stars on them, since these are the x star and the y star, which occur at x and y are plus or minus 2. Okay. So now what we would like to do is analyze the stability. So this is step 2 in our process. So step 2 is to analyze stability. And what you should remember, what we said in the one-dimensional example, is that what you do to analyze stability is you start out very close to the fixed point and you find out what the behavior is like. And so here we do exactly the same thing. So if I go back to our abstract notation, so I'm going to write dx dt, right, is equal to f, and dy dt, sorry, I wrote that badly, is equal to g. Then what we do, and this is exactly analogous to what we did for the 1D case, we're going to write x is equal to x star plus delta, but now I'm going to call it delta sub x because that's the delta that's associated with the x direction. I'm going to write y is equal to y star plus delta sub y. And then we're simply going to find out what the equations look like under these assumptions. And so if I take the first equation is d by dt of x, which is equal to d by dt of x star plus delta x. Now delta x is a function of time. I should have said that before. X star, of course, is a constant because x star is the fixed point. So that is dx dt is the same as d by dt of delta x, and then this, of course, is equal to f, which is now a function of x and y, but x, we're going to say, is x star plus delta x, and y is y star plus delta y. And now, what you do next should not be a surprise to any of you. What you do is you write a Taylor series. So we are now going to expand in a Taylor series. And this, you should notice, is exactly analogous to what we did in the 1D case. And for the 2D case, the Taylor series is given by f of x star and y star plus the partial derivative of f with respect to x evaluated at x star and y star times delta x plus the partial derivative of f with respect to y times delta y. And then, of course, in an exact analogy to what we did for the 1D case, what you should notice is that, of course, this quantity, that is f of x star and y star, is equal to 0 because, by definition, it was a fixed point. So now if I just go to the next slide, I can write what I found in some detail, in a little bit more clarity. So what we just found was that d delta x dt is equal to dxf evaluated at x star y star times delta x plus dyf evaluated at the fixed point. So I'll just write evaluated at star for the fixed point times delta y. So this notation that I just invented right here, this notation basically means that I'm evaluating df dy at the fixed point. And of course, you shouldn't be surprised that if we were to do the same calculation for the other equation, we're going to get dy dt is equal to dxg evaluated at star times delta x plus dyg evaluated at star times delta y. And this I can just write as d by dt of delta x delta y, which is equal to a matrix. I can just write this out as a matrix, dfx, dyf, dxg, dyg. All of these are evaluated at the fixed point, all of these partial derivatives, times delta x, delta y. And this is the equation that governs the stability of the fixed points. And you should note that it's perfectly analogous to the equation that we derived for the 1D case. And actually, I'm going to just do this. I'm going to erase some of this because I'd like to write above this the equation for the 1D case that this is analogous to. So I'll use a different color marker just so that there's no ambiguity. So for the 1D stability, so this is 2D stability. That's what this is. 1D, the analog that you'll remember we derived in class was d delta dt is equal to minus, actually no, it wasn't a minus. Here I need to erase. So it wasn't a minus. So it was df dy evaluated at fixed point times delta. And for this, for the 1D case, we had a simple stability criterion that basically just depended on the sign of df dy. Here we have to actually understand the behavior of this two-dimensional problem. But this two-dimensional problem that we have to analyze should look familiar to you because this actually is exactly the problem. So if I were to use the notation, right, that y vector was equal to delta x, was equal to the vector of two components delta x, delta y, and the matrix A, was equal to this matrix of partial derivatives A, B, C, D, then this equation that we have is that we just derived is exactly the same type of equation as dy dt is equal to A times y, where A is a constant matrix with these constant numbers in them, and that, of course, is the problem that we analyzed in class. So this is the Romeo and Juliet problem. Okay, so now the last step in our little exploration here is to take the formalism that we just derived and apply it to our example. So if you remember, it's been long enough that you might have forgotten our example. So our example was that x star is equal, x dot, the time derivative of x is equal to x minus y, x minus y, I don't know how to use this computer, y dot is equal to x squared minus 4. You will remember that we found that the fixed points, a couple of slides back, we found that the fixed points were at x star, y star equals plus or minus 2, plus or minus 2. So there are two fixed points at 2, 2 and minus 2, 2. And now the question that I would like to ask is, what about stability? Okay, and so you should recall, of course, that this guy, the first equation is F, this guy is G, so I now have to construct the matrix that I'll just call A, which is dxF, dx dy f dx g dy g, and that's just given by, we can just work this out. So let's see, the partial derivative of this with respect to x is just 1. The partial derivative of f with respect to y is minus 1. The partial derivative of the second equation, g with respect to x, is 2x. And this is 0. So that's the matrix. And now we have to evaluate it at the fixed points. So this is because, of course, this was all evaluated at the fixed points. So therefore, what A really is it's the matrix 1, minus 1, and now x is either plus or minus 2. So this is plus or minus 4 and 0. And so with this being the matrix, if we consider the equation dy dt is equal to ay, and we study its behavior, which of course, as you will recall from class, relies on calculating the eigenvalues of the matrix A, then we will find out what the stability characteristics of the fixed point are. And I will continue this example with another video, but I think that's enough for here, and these are in fact the general ideas that you need to start to do your homework.